Hello everybody. We're now starting to see how we can do the solid or start the solid handling work in Aspen Plus, and in this video I'm gonna be like doing the steps that I mentioned in the previous video about the definition of stream classes and the like understanding the substreams in Aspen Plus, how they work, and defining streams. And my focus will be just in the beginning of the work, but I'm gonna follow the procedure or the steps done in the chapter 14 in the textbook Aspen Plus Chemical Engineering Applications by Professor Kamal Al-Maleh. The steps are simple and nice, and there will be a lot of information there in this chapter. If you are interested, or if I missed something, please go and check the and this chapter in the book if you are interested. So the example that I'm gonna be talking about now is crushing of potassium chloride. My focus is not gonna, again, as I mentioned before, it's not gonna be related to crushing. So the crushing will be only to have an operation where we have a feed and the product, and there is a way we can check the difference between the inputs and outputs and how the results are displayed in Aspen Plus in case of dealing with solids. And that's why I'm gonna do the crushing process. So the solid that we are gonna be working with is potassium chloride, and you know, it's a known material that has a known chemical formula. But in this case we want to deal with it as a solid, not a conventional, because we mentioned before the conventional is a material that is dealt with as an active material that has or will be dealt with in the calculations of the phase equilibrium and reactions, but this is not our case. So we're gonna define it as a solid, and this is pretty important, and we will understand in like few minutes how we can see the effect of choosing the type as a solid here. We can define potassium chloride. I'm just gonna do this here for the sake of demonstration. I'm not gonna use it. But I'm gonna define potassium chloride one more time, but I'm gonna keep it as conventional. So I'm gonna call it KCl conventional, so that there is a difference between them. Again, I'm not gonna use this in anything, but just to see how the choice of the type of the material is gonna affect the way it's going to be dealt with in the simulation environment. In the methods section, we need to choose solids because we are going to deal with solids, and it says that it's used for general solids and pyrometallurgy applications. In case you cannot find the solids here, please go here and choose the all in the method filter. I have solids here because I use the solids many times, so it's put as one of the common methods that I use. But in case of using it for the first time, you will not, most probably you will not find it here. Anyway, so I'm now done with the properties environment, and now I'm ready to go to the simulation environment. And what I'm gonna do is define a stream. But before the stream, there is a very important point. So the case that I'm gonna be working with is a solid that I have the particle size distribution of, I know it, and I'm gonna feed it to a crusher so that the particle size distribution will change. So I'm gonna reduce the particle size. The crusher is a machine that crushes the solids. So you have the solid going into the material, it crushes it and produces the solid with smaller particle sizes. It's like a crusher for the nuts and stuff like that. So, but it's on a large industrial scale. So the first thing we're gonna do is to visit the setup tab here, and this is, I think, the first time we go here for a long time, because I think we mentioned this when we started talking about the unit sets, but we never visited this part again. But here it's important because not for the unit set, but for the stream class. And this is what I mentioned before. In our case, I have a solid, an inert solid that has a particle size distribution. So we will go for mixed CI PSD. And to understand more how this choice is going to affect our work, we can go here for stream class and see that the mix CI PSD allows the user to find or work with two stream classes or substreams, I'm sorry, the mixed and the conventional inner particle size distribution. So this is like an important thing that we need to keep in mind, because it's gonna have a lot of impact on the work that we're gonna do. So this is the first thing. There is something that's related to the particle size distribution, but I'm gonna keep it for some time, just few minutes, because we're gonna revisit it. So let's go to the flow sheet and let's call it the feed stream. And when we open the feed stream, we will see that there is one new thing that we never saw before, that the CI tab is now active, and this was never the case before. If we go back, just for the sake of demonstration, if we go back and return this to the conventional, and then we went back here to the feed, this is not active anymore. So it's important to make sure that what you're gonna use is enabled by choosing the proper stream class that will enable you to do what you do. So the first thing that you'll notice is that both tabs are, the mixed and the CI solid, are both active. I'm not active, I mean satisfied. So, and despite the fact that I didn't put any information in either one of them. And the reason is for that is that each one of them, because I don't have to put information in both of them, so only one of them is enough to be filled, so that the stream is totally or fully defined. So it's okay for it to be empty, and it's okay for it to be empty, but at least one of them should be filled. So if you keep it like this and do the rest of the work, then you will have an error that the stream is not defined, despite having both blue. So what I'm gonna do is that I'm gonna define this at the temperature of 25, and I know the pressure of 1 atmosphere. The this is 10 or 100 kilograms per hour, and this is the mass fraction is 1. And we will notice here that the only component that I have here is the KCl. In the mixed substream, you can see both the KCl and the KCl conventional, but here you can only see the KCl. And this is why I defined both, because we now can understand that having the solid defined as a solid, the type of solid defined as a solid in the simulation environment will dictate which one of them is going to be here and which one is going to be there. Now we have the last piece of information that we need to define is the particle size distribution. And to define the particle size distribution, there are actually two pieces of information that we need to define separately in Aspen Plus. So let's go back to the information that we have. So this is the particle size distribution that I have, and we can split it into two pieces of information. The first is the particle size mesh, which is what is the ranges that I'm gonna be defining the mass fractions into. So there is a range from 0 to 1, 1 to 2, 2 to 3, might be 0 to 10, 10 to 20, 20 to 30, maybe 0 to 1, then 1 to 5, then 5 to 20. It might be any random numbers, it might be like equidistant, it might be whatever. So this has to be defined first, and then I will fill it with the weight fraction that I have. And this is what I have. I have no choice of the lower and upper limits here, but I can input the weight fractions here. So this is not what I have. This is in micrometers, and this is in values from 0 to 20 to 8. So it's at 20 microns of increment, which is not what I want to use. So this is not proper mesh for me. So I have an option to edit the Psd mesh from here, or, which is something that I would do in the very beginning, is to go here in the solids and then the Psd, and you can edit it from here. So you can do this even before you do the stream definition. So I have some options here while defining the mesh, which is first, what is the default here is a user specified PSD mesh, which is from 0, 20, 20 to 40. This is manually put, so I can change this to 90. I can change this to 155. Whatever the value that I want, I can change it manually from here. So this is an option. There is another option in case, like our case, that I have an equidistant value, so I know it starts from 0 to 10, and I know this is in millimeter, and I'm gonna ask it to create the mesh, so it's creating the mesh simply without doing any other work. We have the option to, I'm going to keep it like this because this is what I have, and I have an option here to create a new PSD mesh, so I'm going to call it PSD2. And the reason for this is that I might have more than one solid stream, and each one of them has a separate particle size distribution mesh. So in this case, I can choose which PSD mesh that I'm going to use for each stream. So we showed the equidistant. There is a logarithmic which is like the equidistant, but let's say it's from 0.1 to 10, and I have increment of 10 points. So it's exactly like what we do in MATLAB when you have len space and log space. So by linear space, which is the len space, you can choose that you have different values that have equal spacing. But here the values are equal spacing on the log scale, so it's like drawing it on a log paper or something. So this is one other option. There is one last option which is a weird option for me, which is the geometric. And if you see the hint here, it says that covers factor of 2 in particle volume. The upper limit is obeyed strictly. The smallest class will contain the specified lower limit. So I'm gonna run it and see what happens. So let's say it's gonna be exactly like the values I entered for the logarithmic spacing, but you'll have no option to choose the number of intervals, which is weird. But when you create the mesh, it turned to be 20 increments, and the values are very, very weird actually, because they're not distributed in an easy to understand way. And after a lot of like trials, I understood how it works. So the way it works is that the software breaks the values, so that if you divide any one of these values by the one smaller, so let's say 10 divided by 7.93, and then raise it to the power of 3, it's gonna be equal to 2. I don't know why, but this is the way it works. So maybe some people need it, but I don't know how they use it. But anyways, it's an option in case you need it. It's available. But let's go back to this. So we have two PSD meshes, and now let's go to here, and now the PSD is showing the values that I wanted. Now I want to take these values, copy and paste them here. Unfortunately, it's not gonna paste from PowerPoint, so you have to copy from PowerPoint to Excel, and from Excel to Aspen Plus. And this is the way it works. I don't know why, but maybe it's more compatible with it. So the values are here. You can see the weight fraction, you can see the cumulative weight fraction, and one nice thing about it is that you can calculate or draw the profiles for the weight fraction and for the cumulative weight fraction, which is like, to revise, this is exactly what we saw in the last time. So it's a nice thing that you can use if you are interested. Anyway, so now we're now done with defining the stream. We need to define the crusher, where the feed is going to be fed to and broken into smaller parts. You'll find the or the blocks that are related to solid handling are available in 2 tabs. First here is the solids, which is relating to the manipulation of the particles, either by changing the moisture content of it by let's say washing or dryers and crystallization or something like this, or by changing the particle size by crushing, by screening. By screening is not like a control of particle size, it's more of sorting. I'm sorry, of screening, which is a known process where we split the particles according to the particle size. But anyways, but there is a solid washing, there is fluidized bed, granulator, so like size reduction, size enlargement, whatever. But there are other units here for the separation, like the cyclone, the hydrocyclone, Venturi scrubber, the electrostatic precipitator. So all of them are available for solid separation. In our case, we are going to use the crusher, and I'm going to feed the stream or connect the feed stream to the crusher, and then connect the product stream to the results of the crusher. And for the crusher, there might be, or there are some simple things that we can define the crusher by. Again, I'm not gonna use this video or making this video to talk more about the crusher as a block, but just to see how the results are shown in Aspen Plus for solids. So you see, I just defined the product to have maximum particle diameter of 2 millimeters, and now I can run the file. It should be now good to go, and from here you see it's still calculating. Now the results are available, and we can see the stream results. And this is the point I'm interested in, which is defining or seeing the stream results. There are like three things that you'd see here. First, the total stream, which is the summation of all the components or the substreams in the stream. It's going to be the mole flow, the mass flow. Usually what we used to, or previously what we used to see, is that what we have in the mixed substream is exactly what we have in the total substream. However, in this case, the mixed substream will be totally empty because I don't have any components that are defined in the mixed substream, which is let's go back here to the feed, which is the mixed substream here. Nothing, I have nothing here, and that's why in the results I couldn't see anything, because I don't have anything in the mixed substream. The results that we're gonna find are gonna be in the CI-PSD, which is the conventional inert particle size distribution substream. Here you'd see the temperature, the enthalpies, everything that we used to see is gonna be here. The mole flows, the mass flows, everything, and the mole fractions. And the new thing here is the particle size distribution. Keep in mind, if we don't have particle size distribution, like if we use the conventional inert solid substream, then this is not gonna be there. But in this case, you can see the particle size distribution before and after. You see here we had almost 70% for this 4 to 5 and 5 to 6 millimeter range, and the majority of the mass which is almost more than 85%, was more than the 5 millimeters. The crusher reduced the particle size and converted the large particles into small particles, and you see the particles are, it's more than 75% of the, or almost 80%, more than 80% of the particles are, it's even more than 85%, I think, is in the range of 0 to 2 millimeters, and some of them are larger than the 3 or the 2 millimeter range. So this is how the results will look like, and it's important to understand the substreams and how they affect the work that you're going to do, and the inputs that you can put into the software, and where you put the inputs. And it's important to know where you can find the results of the run that you did, because it's a pretty important thing for working with solids. So I hope this video was